4. Forces. On May 27, 1931, a train called Empire Builder encountered the amazing force of a tornado as it moved across Minnesota. The tornado's force was so great that the train was moved along the track at 60 miles per hour. 5 of its 60-ton cars were lifted from the rails. 1 car was lifted and thrown 80 feet into the ditch. Moving heavy railroad cars requires a tremendous amount of force. Forces are created and applied every time anything moves. Forces such as weight are even present when things are not moving. Your body uses force every moment of your life, for every action from the beating of your heart to walking upstairs. Understanding how forces are created and described is fundamental to understanding nature. Forces. We have talked about forces since Chapter 1. However, since force is such an important idea, this whole chapter is about forces. You will learn where forces come from, how they are measured, and how they are added and subtracted. A force is a push or a pull or any action that has the ability to change motion. The key word here is action. Force is an action. You need force to start things moving. You also need force to make any change to an object's motion once it is in moving. Forces can increase or decrease the speed of an object. Forces can also change the direction in which an object is moving. Forces are created in many ways. For example, your muscles create force when you swing a tennis racket. Earth's gravity creates a force called weight that pulls on everything around you. On a windy day, the movement of air can create forces. Each of these actions can create force because they all can change an object's motion. All of the forces we know in the universe come from 4 elementary forces. Figure 4.1 describes the 4 elementary forces. Unless you go on to study physics or chemistry, you may never need to know anything about the strong or weak forces. These forces are only important inside the atom in a certain kind of radioactivity. However, the electromagnetic force and gravity are important in all areas of human life and technology. The strong force. This force binds the nucleus of an atom together. The force is very strong, but only reaches a very short distance. Electromagnetic force. This force acts between positive and negative charges. This force holds atoms together into molecules. The weak force. This force causes some kinds of radioactivity. Gravity. This force causes all masses to attract each other. Your weight comes from the mass of the earth attracting the mass of your body. Mailing a package at the post office. How does the postal clerk know how much you should pay? You are charged a certain amount for every pound of weight. The pound is a unit of force commonly used in the United States. When you measure weight in pounds on a postal scale, you are measuring the force of gravity acting on an object. For smaller amounts, pounds are divided into ounces. There are 16 ounces in a pound. The pound is based on the Roman unit libra, which means balance. That is why the abbreviation for pound is lb, and the word pound comes from the Latin poundus, meaning weight. The definition of a pound has varied over time from country to country. Although we use pounds all the time in our everyday life, scientists prefer to measure forces in newtons. The newton is a metric unit of force. The newton is defined by how much of force can change the motion of an object. A force of 1 newton is the exact amount of force needed to cause a mass of 1 kilogram to speed up by 1 meter per second each second. We call the unit of force the newton because force is the metric system is defined by Newton's laws. The newton is a useful way to measure force because it connects force directly to its effect on motion. The newton is a smaller unit of force than the pound. 1 pound of force equals 4.448 newtons. How much would a 100-pound person weigh in newtons? Recall that 1 pound equals 4.448 newtons. Therefore, a 100-pound person weighs 444.8 newtons. The force of gravity on an object is called weight. At Earth's surface, gravity exerts a force of 9.8 newtons on every kilogram of mass. That means a 1 kilogram mass has a weight of 9.8 newtons. A 2 kilogram mass has a weight of 19.6 newtons, and so on. On Earth's surface, the weight of any object is its mass multiplied by 9.8 newtons per kilogram. Because weight is a force, it is also measured in units of force, such as newtons and pounds. People often confuse weight and mass in conversation. However, weight and mass are not the same. Mass is a fundamental property of matter measured in kilograms. Weight is a force caused by mass. You have weight because the huge mass of the earth is right next to you. It is easy to confuse mass and weight because heavy objects, more weight, have lots of mass, and light objects, less weight, have little mass. Always remember the difference when doing physics. Weight is a force measured in newtons that depends on mass and gravity. A 10-kilogram rock that has the same mass no matter where it is in the universe. A 10-kilogram rock's weight, however, depends completely where it is. On Earth, the rock weighs 98 newtons, but on the Moon, it only weighs 16 newtons, figure 4.3. The rock weighs 6 times less than the Moon because the gravity is weaker on the Moon. Formula, figure 4.4, weight equals mass times the strength of gravity can be arranged into 3 forms. You can use this formula to find the weight, mass, or the strength of gravity if you know any 2 of the 3 values. The direction of a force makes a big difference in what the force does. That means force is a vector, like velocity or position. To predict the effect of a force, you need to know its strength and its direction. Sometimes the direction of a force is given in words such as 5 newtons down. In diagrams, arrows are used to show direction. Forces are assigned positive and negative values to tell their direction. For example, suppose a person pushes with a force of 10 newtons to the right. The force vector is 10 in. A person pushing with the same force to the left would create a force vector of negative 10 in. The negative sign indicates the negative 10 Newton force is in the opposite direction of the positive 10 Newton force. We usually choose positive values to represent the forces directed up and to the right, north, or east. It is sometimes helpful to show the strength and direction of a force vector as an arrow on a graph. The length of the arrow represents the strength of the force. The arrows point in the direction of the force. The x and the y axis show the strength of the force acting in the x and y directions. When drawing a force vector, you must choose a scale. For example, if you are drawing a vector showing a force of 5 newtons pointing straight up, y direction, you might use a scale of 1 centimeter equals 1 newton. You would draw the arrow 5 centimeters long pointing along the y direction on your graph. A 5 newton horizontal force would be drawn with a 5 centimeter line shown below. And springs are often used to make and apply forces. Ropes are used to transfer forces or change their direction. Springs are used to make and control forces. The pulling force carried by a rope is called tension. The tension always acts along the direction of the rope. A rope carrying a tension force is stretched tight and pulls with equal strength on either end. For example, the 2 people in the diagram at the left are each pulling on the rope with a force of 100 newtons. The tension in the rope is 100 newtons. Ropes or springs do not carry pushing forces. This is obvious if you have ever tried to push a rope. Springs are used to make or control forces. A spring creates a force when you stretch it or squeeze it away from its natural shape. The force created by the spring always acts to push or pull the spring back to its natural length. When you stretch a spring, it pulls back on your hand. When you squeeze a spring, called compression, the spring gets shorter. As it gets shorter, the spring pushes back on your hand. The force created by the spring is proportional to the amount the spring is stretched or compressed. If you stretch a spring twice as much, it makes a force that is twice as strong. Pause here and answer the questions.